Okay, let's begin. So today I want to talk about a little bit about ultra products again, generalization of ultra products and Walsh's theorem. So before we do that, I want to show you something very interesting about the structure of formulas. Okay, so let's start with a particular formula. In appropriate languages, okay, the languages are going to be different. So the first formula I am writing down is this: for all W1, W2, G W1, W2 is equal to G W2, W1. What does this represent? Commutativity of the function symbol G. Okay, or its interpretation, fine. Then another thing I am going to write down is this: for all W1, W2, there is a bracket R W1, W2, conjunction R W2, W1. This thing implies W1 is equal to W2. What does this represent? Antisymmetry of the interpretation of the relation symbol R. And last one I am going to write down is for all W1, negation W1 equal to 0 implies there exists a W2 such that G W1 W2 is equal to E and G W2 W1 is also equal to E. What does this represent? Multiplicative inverse, yeah, in an appropriate language. Oh sorry, I made a slight error here. I should not be writing 0, I should be writing C. Okay. Okay, so these are three different types of sentences. The first one is called a universal Horn sentence. Okay, so what is its form? Its form is very simple. It's bunch of universal quantifiers in the front, and inside it is an atomic formula. Okay, then the second one is called a strict Horn sentence. It has this particular form. So a bunch of universal quantifiers in the front, and then inside there is a conjunction of atomic formulas, some finitary conjunction, and this conjunction, whole conjunction, implies another conjunction, another single formula. So in particular, if I choose n to be equal to 0, what do I get? The universal Horn sentence. Okay, so strict Horn sentence, yeah, it's Horn as in these horns, yeah, it's a name of a person. Okay. And the last one is not a strict Horn sentence. Are you all convinced? The last one has a negation of an atomic formula and implies something else, and then there exists is inside. Even if I use the standard logical equivalences to bring this there exist out, still I will not get anything nicer. Yeah, there exist will come out as there exist. So it's not in the universal form like universal quantifiers and then inside something else happens. Now I am also going to ask you something related to this. So this is like 1, 2 and 3. Yeah, maybe I should write here that phi i's and psi are atomic. Okay. Now the first one is satisfied, let's say, by a group, yeah, when G is interpreted as a binary function. So is the cross product of two groups a group? I mean, if you don't know what a group is properly, then just think about R plus 0. R plus 0 cross R plus 0. Is that a commutative group? Does it satisfy commutativity? How is this sum defined in R cross R? Component wise. Okay, so R plus 0 cross R plus 0 is commutative. Okay, so in general, any interpretation, if you have two structures for which there is some G which is commutative, then I take cross product of those two structures, the product structure, yeah, we have defined product structure properly, then that will satisfy this commutativity property. Okay, second one, if I take two different posets, so P1 less equal cross P2 less equal. Yeah, this is also a product of structures. Is it still antisymmetric component wise? If in both components you have this, yeah, means A1 B1 is less equal A2 B2 and A2 B2 is less equal A1 B1. Then A1 B1 is equal to A2 B2, right? Okay. So this one is antisymmetric. Third one, on the other hand, if I take real numbers with addition, multiplication, minus 0, 1, our usual thing, and I take its cross product with itself, yeah, we have already seen this is not a field. This is the field axiom. It says that every non-zero element has a multiplicative inverse. Whereas this one is not a field because 1 comma 0 multiplied by 0 comma 1 is 0, or 1 comma 0 is a non-zero element but it doesn't have a multiplicative inverse. Is that clear? Okay, so this is not a field. Similarly, can you tell me the distinguishing property between linear orders and partial orders? Trichotomy. So fourth one I will write trichotomy, and what is the form of that sentence? For all W1, W2, there exists a W3? Trichotomy. Either RW1, W2 or RW2, W1 or W1 is equal to W2, just to be safe, even if it is interpreted as a strict order. Now, if I take cross product of two linear orders, yeah, we did that. Cross product of a 2-element linear order with a cross product of 3-element linear order. Sahil wrote that on the screen. Was it a linear order? No. So, cross product of two linear orders So L1 less equal cross L2 less equal does not satisfy trichotomy. So again, look at the form of this particular sentence. This is not a Horn sentence. It's not a strict Horn sentence because it uses universal quantifiers and then disjunction inside. Okay, so what is important here is that if your sentence, if your axiom happens to be a universal Horn sentence, then it is preserved under products, and conversely also it is true. Okay, so a sentence is a universal Horn sentence if and only if it is preserved under generalized products. Okay, now I am using a slightly different word, but anybody has any problem with this? Well, perhaps you can ask the question, can't you find out anything which is logically equivalent to, let's say, trichotomy, and which is a universal Horn sentence? But the answer is you can't. Yeah, and that is because it is not preserved under products. Because this is an if and only if statement. So more generally, yeah, I mean, now let's go and do some theory. So all of you remember this structure, product of mi, I in I. Yes, this is the product structure. If I quotient it out by a relation, yeah, I mean, instead of this, maybe I should write. So you remember this was an ultra product. And at one point we did check that tilde u, yeah, tilde u is an equivalence relation. Equivalence relation on the product of the sets, underlying sets. And if you remember the proof of this equivalence relation, then reflexivity, transitivity and symmetry were the three conditions that we checked. But in none of those conditions we actually use the full definition of an ultrafilter. Every time whatever we used was, oh, it should be closed under intersections, finite meets, and it should be closed under upper bounds. We never used, so we only used, yeah, but we only used that U is a filter. So my point is that even if you relax this condition a bit, even if you don't say it's an ultra filter, you just say it's a filter, then also everything will go through. So the same construction, the ultra product construction, goes through if the ultra filter U is replaced by a filter, say F. Can you give me one very simple example of a filter? Just singleton top element, yeah, singleton I, that's a filter, yeah, because it is non-empty, it is proper subset, it is closed under upper bounds because it only has one element, and it is closed under finite meets because meet of the top element is again itself. So, in that case, if I construct this relation, what does this say? Two things are equivalent, two tuples are equivalent if and only if the set of indices where the tuples agree lies in I. I mean is equal to I. Yes? Maybe if you are confused, I will write down. Yeah. In particular, if f is equal to singleton I, then ai I in I is f equivalent to bi I in I, if and only if the set of all indices such that ai is equal to bi, this one belongs to f. But what is in f? Only capital I. So, if and only if for all I in I, ai is equal to bi. Well, this means that we are not quotienting out by any non-trivial equivalence relation, it is just the identity. So, therefore, product of mi I in I modulo f is equal to just the product of mi's. We are not identifying anything here. So, this shows that if you replace an ultra filter by an arbitrary filter, then product is also a filtered product. An ordinary product is also a filtered product. Okay. Oh yes. Here I should write the name, yeah. To get a reduced product. Yeah, this is the name. Yeah, this is the name of that. So, this is I in I modulo f. Yeah, so ultra products are generalized to reduced products, and reduced products, it is not just one reduced product. Yeah, if you change your filter, you will get another reduced product. And one particular example of a reduced product is just the product. Okay. So, for every reduced product also, yeah, I mean let me write that theorem down. So, suppose L is a language and I is a non-empty set. Mi f a filter on I, then mi I in I an indexed family of L structures, and phi is in SL. Then the reduced product oh sorry, I should not have said this. I will change it slightly. Yeah, the filter is not given yet. Okay, then phi is logically equivalent to a strict Horn sentence if and only if for all filters F oh wait, I should say something more in this in the hypothesis, and Mi satisfies phi for all I. Okay. If and only for all filters F, the reduced product satisfies phi. I already gave you lots of examples, yeah, that antisymmetry, commutativity, associativity, identity, they are all examples of strict Horn sentences. And if your component structures satisfy the strict Horn sentence, then for all reduced products that will happen. Yeah, because this is an if and only if characterization. And you can see how beautifully you can know about the form, the syntactic form of a sentence based on a model theoretic property. Okay, now once again focus on this red sentence. What does this say? That we have only used that U is a filter. Then why are we talking about ultra filters at all? Where exactly was it used in Walsh's theorem? So I am going to show you that part now. So if you remember Walsh's theorem, I am not going to write down full statement, but just this. So product of Mi I in I modulo U satisfies phi x, let's say phi at H1, H2, Hn, their equivalence classes, if and only if the set of indices such that Mi satisfies the individual component structure components H1i up to Hni lies in U. We never really proved this. Yeah, I told you that the proof is very simple. It's just induction on the complexity of formulas. But I am going to point out your attention to one particular proof, one particular part of the proof. So let us say, suppose by induction hypothesis, the conclusion, I mean the statement is true for phi x bar, and we want to show it, we want to prove the statement for negation phi x bar. Okay, so negation is the only part where we really use that it is an ultra filter. So when will that happen? Okay, so what do we need to start with? So let us look at the definition. Yeah. So product of Mi I in I modulo U satisfies negation phi at these equivalence classes of choice functions. If and only if, yes, I am going to write this. What can you say about the product satisfying phi at this collection? It does not. Okay. Okay, so by induction hypothesis, what do you get? This does not satisfy. So by induction hypothesis for phi, what do you get? That this collection of indices is not in U, such that Mi is not in U by induction hypothesis. Okay. Now comes the important property. If this set doesn't belong to U, then by the ultra filter property, what belongs to U? Its complement. Yes, this is the crucial step where we use that the set of i's such that Mi doesn't satisfy. I mean, maybe I should write down one more thing. Yeah, so if and only if the complement of this set belongs to U by ultra filter property. Okay. Now, this is same as the set of indices where, what should I write now? Mi doesn't satisfy phi, Hni belongs to U. Well, what is the meaning that Mi doesn't satisfy phi? Mi satisfies negation. Very good. So now we are done. So Mi satisfies negation phi at these components, and this is precisely what we wanted to show. Okay, all the remaining things there exist, and conjunction, everything is simple. But this is the only crucial property where we use that it is an ultra filter, and that's why Walsh's theorem is a very strong statement. It says that if majority of the structures, component structures satisfy your property phi, then the ultra product will also satisfy it. But we just saw on the previous slide, to contrast that even if all of the structures satisfy phi, the reduced product may not satisfy it unless it is a very particular type of sentence. It is a strict Horn sentence. Okay, so that's why R cross R is not a field. Yeah, and we had to work hard and to get hyperreals to quotient out by an ultra filter. You understand this part now? And I also gave you a sketch of some part of the proof. I mean, this is an actual proof of the negation part. Yeah, there is no point in writing down the full proof of Walsh's theorem. Let's go ahead then. Fine. So now we are going to talk about a concept which was originally introduced by Oswald Veblen in 1904. So, if you are given a theory, now what can you do with that theory? You would like to find its models. You know it is satisfiable, you would like to find its models. And once you know that models exist, you would like to understand all its models. Well, obviously, you cannot understand all the models like individually, because you can always change the names of elements in that model. So, up to isomorphism, you would like to understand all the models, right? So, Veblen was also thinking like that in 1904, yeah, very early, more than 100 years ago now. So, he said a theory gamma is categorical if any two of its models are isomorphic. Okay. Now, can you give me one example of a theory which is categorical? Sets with n elements. Yeah. If set with n elements is the theory, then sigma n is the sentence that we write. So, if one model satisfies sigma n and another model satisfies sigma n, then there are n elements and you can't really say anything else about them. You cannot distinguish between those two elements, and then there is a bijection between any two n element sets, right? So, therefore, any two models are isomorphic. That bijection is an isomorphism of structures. So, therefore, yes, so for example, gamma n equal to singleton sigma n is categorical. And it wasn't really surprising, but Veblen and all his successors only found examples of categorical theories which have finite models. Okay, so then in 1917 or 18, just after First World War, so Leeuwenheim and Skolem, I think it was just Leeuwenheim in the beginning and then Skolem added something. So this is around 1917. So they proved their theorems, yeah, which says that if your theory has one infinite model, then it has infinite models in all cardinalities, bigger equal the cardinality of the language. Yeah. If a theory gamma has one infinite model, then for all kappa bigger equal the size of L, there is a model of size kappa. So, if two different models have different cardinalities, can they be isomorphic? Obviously not, yeah, because there can't even exist a bijection. So, for isomorphism, existence of a bijection is the basic requirement. So, therefore, you cannot have any categorical theory, right. So, no categorical theories with infinite models. Okay, so this was a very easy consequence of that, but a mathematician doesn't really stop. If you get a counter example, then you modify your definition. Okay, so then people said, why not study a graded version of categoricity. What's a graded version? That you fix a cardinality and then ask whether there is a unique model of that cardinality up to isomorphism. So this is the definition of kappa categoricity. So let kappa be a cardinal say that a theory gamma is kappa categorical if any two models of size kappa are isomorphic. This one is more believable, yeah, because now you can at least talk about bijections. Yeah, the problem with Leeuwenhoek-Skolem theorem's conclusion is that their cardinalities are very different. So it doesn't really make sense to ask for something nice. Okay, so when kappa is aleph naught, yeah, this is just a note. Yeah, so note, if kappa is equal to aleph naught, then the literature mentions omega categoricity instead of aleph naught categoricity. Yeah, perhaps when this discussion started, the notation aleph naught was not in practice. So therefore, they only talked about omega categoricity. Omega and aleph naught are the same as ordinals, they are the same. Yeah? But if you read something, then you will find omega categoricity to be a more popular choice of name. Okay. Now, let us, if we have defined something, then let us give an example. So, the first example is that the theory of R vector spaces. This is kappa categorical for all kappa bigger equal 2 to the aleph naught. I think you know the proof of this statement. So can somebody spell it out for me? What is a model of the theory of R vector spaces? R vector space. So two models of size kappa, how are they determined? Sorry, I should not say this, I should say bigger. Two models of size kappa bigger than 2 to the aleph naught. How are they determined? See, I am not talking about R and R square. R and R square have the same cardinality. Yeah? And are they isomorphic as vector spaces? Why? Different dimensions. Very good. So dimension is the key. Whereas if you go to infinite dimensional real vector spaces, the dimension is simply a cardinal number. And we know what that dimension has to be. I mean, do you remember that we proved that real numbers must have, or real numbers thought of as a rational vector space has uncountable bases? You remember that? Okay, so similarly, if I am given an R vector space of cardinality kappa strictly bigger than 2 to the aleph naught, then what will be the size of the basis? You can show its kappa. So therefore, any two vector spaces of cardinality kappa bigger than 2 to the aleph naught have basis of size kappa, and any two sets with size kappa are in bijection. So therefore, this is kappa categorical. You can set up a nice bijection. But in the cardinality 2 to the aleph naught, this is not true. Yeah, because you already know there is real numbers, then r square, then r cube, and r to the power 4, and so on and so forth. Another thing, you remember this, and I am going to add a 0. Yeah, so this is the theory of algebraically closed fields with no multiplicative torsion element, no non-zero multiplicative torsion element. What do I mean by that? That if a is not equal to 0, then that implies that a to the power n is not equal to 0. Okay, so this is what I mean. So this is kappa categorical for all kappa bigger than aleph naught. So all uncountable cardinalities, this is kappa categorical. So do you know any uncountable algebraically closed field satisfying this property? Real numbers. Real numbers, are they algebraically closed? Because x square plus 1 equal to 0 doesn't have a root. So they are not algebraically closed. But complex numbers are. So complex numbers, what is their cardinality? 2 to the aleph naught. So it is strictly bigger than aleph naught thanks to Cantor's theorem. Yeah, so this one is also, like complex numbers are the only algebraically closed fields of characteristic 0, that's the 0 is written as characteristic 0 in cardinality 2 to the aleph naught. Yeah, very interesting statement. In fact, yeah, and I will give you more examples, but at the same time we saw yesterday, yeah, but gamma ACF 0 is not aleph naught categorical. Yeah, because yesterday we saw this q bar alge, okay, then I can also take, yeah, this is perhaps a bit too much for you, but if I take polynomials with coefficients from q bar alge and I take quotients of them, so these are called rational functions, a polynomial divided by another polynomial which is non-zero. Yeah, so this is px bar, px divided by qx, where qx is not equal to 0. Not identically 0 polynomial. Yeah, so this is called the field of rational functions. So this is another example of an algebraically closed field. Similarly, yeah, I can always attach another variable and I can also say q bar alge x1, x2, xn for any n variables. So you take polynomials in n variables, take their quotient rational functions, and that is also an algebraically closed field. Okay, so these are different algebraically closed fields. They are not isomorphic because the number of variables is called the transcendence degree. So the transcendence degree in this case is 0, in that case is 1, 2 and n. Okay, so transcendence degree is different, so they cannot be isomorphic. So this is not true. However, yeah, and perhaps we should look at one most important example, yeah, the third one, that is gamma DLO unbounded. So this is Aleph naught categorical. Do you remember what was the first theorem that we proved in the class? The very first theorem. Huh? Cantor's theorem. Very good. So this one is also due to Cantor. Okay, so this is called Cantor isomorphism theorem. So unbounded, you understand? Yeah, it doesn't have a least element, it doesn't have a largest element. Okay, so I am going to give you a sketch of the proof of this. Yeah, I won't do it. So suppose L1 and L2 are countable unbounded dense linear orders. Okay, so it's dense linear orders which are unbounded have this property that between any two distinct elements there is a third element, below any element there is another element, and after any element there is another element. So these are the properties, and these are countable, that is given. What does countability entail? That there is a bijection with natural numbers. So bijection with natural numbers means, which means that we can list all the elements. So let us list. So L1 I am going to list as A0, A1, A2, A3 and dot dot dot. Then L2 I am going to list as B0, B1, B2, B3 and dot dot dot. Okay. Now I am going to describe, I am going to construct a bijection between these two. Okay. The idea is called back and forth method. This is a very interesting and useful technique in mathematics. Okay, so it's like a ping pong ball match. Okay, so back and forth method. You first say that A0 is mapped to B0. Okay. Then you look at the least index here that is not used. What is that? B1. B1 is not used. Now you compare. Yeah, this is the comparison part. So either B1 and B0, what can happen? Either B0 is less than B1 or B0 is bigger than B1. Okay. Now, if this happens, then where do I map to B1? Where do I map B1 to? So A0 is paired with B0. Now B1 is bigger. So in this list, I find the first element which is bigger than A0. Why does it exist? Because it is unbounded. So suppose A3 is the least index such that A0 is less than A3. Then what will I do? I will map B1 to A3. Now one round of back and forth is done. See, first I mapped something from L1 to L2. Second time I mapped something from L2 to L1. Now I will again choose the least unused index. What is that? A1. Okay. Now A1 I am supposed to map somewhere, but I already have the configuration of chosen elements. Now suppose A0 and A3 and A1. Now I have to look at where exactly A1 lies. So maybe it lies between these two, or maybe it lies like this, or maybe it lies like this. Whichever property, for the first one I will have to use density of L2. Yeah, by density of L2 I can find an element between B0 and B1 and which has the least index. So I will map it to that. If the first one is true, then I will use that it is unbounded below, and for the last case I will use that it is unbounded above. But I will always find one element, and by unbounded, because we are ordering, so this is well ordering, I will always find the least bi with this property, and then I can map, let's say, this one to this one, and then again the ball is passed on to L2, and then you complete this, and you just have to argue that you have exhausted all the elements on both sides. You understand? So this will set up an order preserving bijection between two linear orders. So this was the original argument of Cantor. Yeah, that's why it's called Cantor isomorphism theorem. So rational numbers are a dense linear order without endpoints. Similarly, any open interval 0, 1, yeah, this is isomorphic. Rational numbers and 0, 1 are isomorphic. I mean not this whole interval, but intersection with rational numbers. The rational interval 0, 1, rational interval 2, 3, they are all isomorphic to rational numbers as a model of gamma DLO unbounded. On the other hand, if you had one lower bound, let's say, it is bounded below but unbounded above, then you always map in this process the lower bound to lower bound and you continue with the process. Get it? And similarly, if it is bounded on both sides, then also you map lower bound to lower bound, upper bound to upper bound, and in between you just play the same game. So there are 4 different theories which are categorical. And if you remember Wash-Watt test, it talked about something like categoricity implies completeness. Okay, so we are going to start tomorrow with the proof of Wash-Watt test. And we'll prove that this particular theory is complete. Similarly, this theory, gamma ACF 0, is complete.